So excited to get going here. Um, Eric, can I get you to read the antitrust statement quick?
Sure can. Antitrust and Compliance Statement. The Advanced Water Heating Initiative, AWHI, is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product or accessory.
Awesome. Thanks a ton. So for our agenda today, we're going to go through a couple of AWHI updates, a little bit more than usual because Heat Pump Water Heater Day is just around the corner next month. So definitely going to have some updates for that. And then we'll have Lucy Matthews from WattTime talking about unlocking impact, the role of heat pump water heaters in reducing grid emissions. WattTime has a lot of really cool data, so we'll get to see some of that and discuss some of Lucy's work over there. And then Madison Johnson from Ecotope will go over the results of a fairly recent study on quantifying load shifting potential for central heat pump water heaters. So with that, I'll go into a couple of AWHI updates. We just had a really great high performance Windows webinar. If you're interested, I'm personally not working on Windows so much, but organizing the webinar was a bunch of fun and the speakers were truly top notch. So definitely recommend that. If you're, looking to get a little more into other building science topics, it's always super cool. And then upcoming next week is a webinar on efficient tiny homes. So you can register by going either to the NBI events page. You can also go to AWHI and the banner should be there for your sign up. So pretty easy to do and should have some great speakers on that, including Sean Armstrong from Redwood Energy, who's always awesome speaker. Joe Wachunas, my colleague, just recorded his second episode of Heat Pumps and Cardigans. The first one was focused on GE's new GeoSpring product, and the second is focused on the new LG heat pump water heater. So both are interviews with the manufacturer. They go into a ton of depth on these new exciting products. GE has a lot of cool things going for them for load shifting specifically because they can go up to 160 degrees. And then this new LG is really tailored for being kind of a visible product in the home, almost like a refrigerator. So the aesthetics are really top notch here. I've also heard that A.O. Smith came out with a recent product that can go up to 155. So a lot of good news on the load shifting front for heat pump water heaters recently. So yeah, definitely encourage you to check these out. They'll be on YouTube on the AWHI website, or you can look up heat pumps and cardigans. I don't think anything else has a similar name, so should come up. Importantly, we have Heat Pump Water Heater Day coming up on October 23rd. That is going to be the main day of virtual events. We have Jigger Shaw as a keynote speaker, which is great. It's a fun theme this year. It's Go-Go Heat Pump Water Heaters, kind of based on the Inspector Gadget cartoon from a while back, but the theme just kind of fit heat pump water heater as well, because it's all about cool tech. There are also other events over the course of Heat Pump Water Heater Day week. So earlier in the week, we'll have a session focused on heat pump water heaters in restaurants. We'll have a load shifting session, so definitely make sure to catch that early in the week. If you go to the AWHI homepage, you'll be able to find all this info and register for relevant events. We do have one in-person event too, which is going to be Heat Pump Water Heater live training in San Jose at the Pipe and Trades Union Hall building, which is sponsored by PG&E. We'll have a bunch of cool sessions there, including talk about recirc pumps, central systems. A bunch of the new residential systems will be on display with sales reps. And Jeff Wicks, are you on the call today? No problem. Well, Jeff's been a great organizer of this event. I think you all probably know Jeff, and he'll be there helping run the show on this day. So yeah, again, this is October 22nd, just the day before Heat Pump Water Heater Day. So if you are in the Bay, this is a free event to get to chat with a bunch of manufacturers, see this tech in person, and there'll also be a opening plenary on AI in the building world. So definitely check that out. It's free. There'll be great catering and free lunch as well. So highly encourage you to sign up and join. And then last slide here, there's also a heat pump water heater day giveaway from Bosch. So you can enter that contest and potentially win a free heat pump water heater. And then very last thing here, we have an Excellence in Water Heating Awards. So that's going to be, there are nominations before September 29th. If you want to put in a product or a company you think has been doing great, I'm going to pop this link in the chat. You can check it out further, and we'll announce the winners during Heat Pump Water Heater Day. Any questions on Heat Pump Water Heater Day or events around there? Cool. Okay. Well, we hope to see a bunch of you there. Oh, Austin, yeah, you had to chat here. Has it been mentioned to this group that a draft for the implementation guide for CTA 2045B and point 4 is currently out for public comment? Austin, do you want to say a little more about that?
Yeah. So we're not directly involved, but we were made aware that the EcoPort standard is getting an implementation guide edition in the form of the CTA 2045.4. There's a draft that's currently out. I believe public comment closes September 29th.
Cool. Okay, great. Yeah, well, if you have a contact there, would you mind looping me in and maybe we can have someone chat about it on the next working group?
Yeah, I could do that.
Perfect. Thanks a ton. Yeah, great update. And yeah, folks, we always encourage updates here. If you have news or discussion points you want to bring, then you're always more than welcome. Awesome. Well, with that, I'm going to turn it over to Lucy to talk about WattTime and some of her research.
Awesome. Thank you, Noah. Let me just see if I can get loaded up here.
Well, I just stopped sharing.
Can you see my screen okay?
I do indeed.
And you hear me okay?
Yep, sounds loud and clear. Perfect.
Fantastic. Well, thank you so much, Noah. Hi, everyone. Really excited to be here today. My name is Lucy Matthews. I'm a partnerships manager here at WattTime, sitting on the partnerships team. I also have a colleague on the line as well, Henry Richardson. He's a senior analyst here at WattTime. So he'll be on hand to answer any technical questions you might have at the end. And if you're unfamiliar with WattTime, we are an environmental tech nonprofit, and at a high level, we can tell you the causal impact of using or creating a kilowatt hour of energy at any given time or place. So I'm really excited to be talking to you all today as your specialists in sort of this space. So really excited to talk about how we think heat pump water heaters can help to reduce emissions. And just a little bit of housekeeping before I start. If you can keep questions to the end, there is a method to my madness on how I'm presenting this. So please keep questions to the end. It should only take 15 minutes or so. So there'll be ample time at the end to hopefully have a lively discussion. So just a quick overview of the agenda. So I wanted to talk through some trends we're seeing across the electricity sector and how we think heat pump water heaters can be allies of the grid. So a big trend we're seeing across the electricity sector are grids being tested, and this is happening worldwide. There is pressure to increase supply due to a rise of electrification, due to EVs, AI, data center growth, all while trying to maintain stability, especially in the face of more frequent and dramatic climate disasters. And then at the same time, there is also this pressure to integrate renewables to the grid at record speed to reduce emissions. And the blackout in Spain and Portugal earlier this year really shows what happens when all of these factors collide at once. And then on top of this, we are literally throwing away renewable energy in massive amounts, demonstrated here in Spain. We're also seeing this in Germany, where renewable curtailment how we throw away energy that can't be used, renewable energy. It's also increasing in Germany, and we can actually quantify that now as this huge economic loss. And this isn't just a problem in Europe. We're seeing this across the US as well, demonstrated more consistently in Texas, as shown here, and in California. And to put this into perspective, in March of this year, renewable curtailment in CAISO, which I'm sure you're aware is the largest grid in California, curtailed 900,000 megawatt hours of clean energy in 1 month. And to put that into something more tangible or digestible, that's enough energy to power almost 1 million heat pump water heaters for an entire year. So enough energy was thrown away, clean energy was thrown away in 1 month to power almost 1 million heat pump water heaters for an entire year. So in a world where demand for electricity is growing, it seems implausible that we are throwing away clean energy, especially when that energy could have been utilized if devices with load flexibility could better align with those periods. But how do we do that at scale? So when we think about timing device use with cleaner times on the grid, we need the right signal to tell us when that time is. So you are likely all very well versed on how the electricity grid works, so I will not insult your intelligence or spend too long here, but this is a hypothetical dispatch stat. So to provide energy in response to demand, resources are dispatched throughout the day to meet that increase in load. And this generally works from cheapest available resource up to the more expensive resource. And that energy resource that comes online to meet that increase in demand is called the marginal unit. So in this example, the marginal unit is coal, and the causal impact of using electricity at this time is 2,000 pounds of CO2 per megawatt hour. So this was at 4 a.m. This is the same dispatch stat on the same day, but at a different time at 5 p.m. And the causal impact of using electricity at that time is 1,000 pounds of CO2. So really big difference in the emissions amounts when you look at the same grid on the same day at different times. I also wanted to call out here the lack of correlation between price and carbon. I think sometimes low price can equal lower emissions. That can sometimes be true, especially as more renewables are being curtailed, leading to even lower prices. But price signal isn't enough alone to truly optimize for lower emissions. And when you look at consumer price of electricity, there can sometimes be an even further disconnect. And I wanted to demonstrate here how dynamic a marginal signal can be over time. So here on the left, you can see how the marginal signal changes by minutes and how it varies throughout the year as seasons change. So really understanding this is critical to drive in real world impact. And when you look at other signals, like an average signal, for example, this visual on the right, it calculates the overall carbon intensity, but it really fails to reflect real-time grid behavior and how it reacts to changes in demand. A marginal signal can also capture moments of renewable curtailment in real time. So again, if we can align flexible devices with these moments, they can soak up that excess renewable energy instead of letting it be thrown away. And because this signal can be volatile, as demonstrated on the previous slide, this really works best when this can be automated. So the end user doesn't want to plan their showers or worry about the best time to plug in their EV. They just want a hot shower when they want it and a full battery in their car when they want to drive it. And automation makes this possible. We want people to choose the environmental impact they want to have without adding effort or forcing them to change their routines. And that's the challenge. That challenge was really the catalyst for us developing automated emissions reductions, or AER. really making it possible for people to choose cleaner energy. And the automation piece is key because that really leads to higher user participation and greater emissions reductions. So I wanted to show what AER looks like in action. So what you're looking at here is an example of an actual EV charging session with one of our partners. So I know EVs are not the focus of today's topic, but this is a really great example to really visualize how this optimization works in real time, and it can be replicated for multiple different devices. So AER works best when the device has load flexibility. So what you're looking at here is a charging session. The blue is when the car was plugged in and unplugged. So the user plugged in just before 6 p.m., unplugged around 8 a.m. So around 14-hour window for us to be able to optimize this charging session. And as you can see, the bar in gray, that is if the car was charged as soon as it was plugged in without any optimization, it would have charged for 2 hours and then stopped. The yellow bars here is when it has charged based on optimization, and the gray line is the emissions rate. So when the emission rate is low, you can see the yellow bar aligns with that to show that it's charging when the emission rates drop. And then when the emission rate goes back up again, it stops charging and then starts again when emission rates drop again. So again, this really proves the impact without impacting convenience or comfort for the end user. They've plugged in, gone to bed, got back up in the morning and got in their car, and it's charged to the point of charge they wanted it to be, and they know that it's been charged with cleaner energy. And what this results in is an 87% reduction in avoided emissions compared to the baseline. And we're seeing this concept scale fast. Over the last few years, we've seen household names adopt this optimization in their devices for different customer programs and product features. And this kind of automation is now active in over 1 billion devices globally in a variety of different devices. It's available in iPhones, EVs, batteries, commercial buildings, home thermostats. And we really think that heat pump water heaters have an untapped potential. So when we think of the perfect candidate for AER, we are looking for an IoT device that has load flexibility and a large window of opportunity to optimize electricity use with cleaner times. And heat pump water heaters checks all of these boxes and more. What makes them uniquely powerful is the way they act as a thermal battery. So that adds an even greater window of opportunity on when the water can be heated and available when needed. So really makes them an exceptional candidate for AER. And I also wanted to call out that this kind of optimization doesn't have to be standalone. It is possible to optimize for multiple objectives. And I think, especially in today's world, people are very price sensitive. So being able to operate devices to align with the cheapest times on the grid is also incredibly important. And we have a way to do this, and we've worked like this with other partners as well. And this is what it looks like in practice. So here we're co-optimizing for price and emissions. And as you can see and probably aware of, retail rates tend to not have a lot of variance. They're usually pretty flat other than time of use or peak periods. But then when you look at an emissions rate, that tends to be a little bit more volatile and variable. And there's several different ways you can do this co-optimization to align these two objectives. And one way is to assign a dollar weighting to carbon to help in determining when to use energy. So in this graph on the right here, the blue section is the base electricity rate and the purple is the marginal. Combining them together by adding a dollar value to a signal, the periods of time when marginal emission rates are low and prices are low is highlighted as the best time to use energy. So this is what it looks like in theory, but we have started to test this in practice with heat pump water heaters. We have recently supported UC Davis in a pilot to operate heat pump water heaters for low cost and low emissions. So doing co-optimization in the real world. The goal of this project is to develop an open source framework to optimize heat pumps for low cost and carbon without impacting comfort. This project is still in flight and is due to complete next March, I believe. There are a few early results I can share with you, but I wanted to quickly walk through what the project has entailed. So they have built an optimization function integrating price and emissions. And here you can see the elements of the cloud-based MPC. And here's kind of a visual of how the implementation actually works. And I'll talk through this pretty quickly here. Information is collected from multiple sources at the top there, from different APIs and the manufacturer. And that data is sent to the supervisory MPC to make the scheduling decisions. And then that information is pushed back to through the cloud infrastructure to the manufacturer scheduler. In this case, it's Econet, Rheem. And that pushes the control to the heat pump water heater on site. And then that information is sent back through the system. And in the lab testing results, it showed a reduction in cost and peak runtime. And you can see sort of the results here. But I also wanted to mention that the MPC and infrastructure is all open source and available for use. And I think we could follow up with all of those materials after this if anyone is interested. And here are the early results I teased. So at a high level, this project has already proven that optimizing for multiple objectives is possible, all without imposing on the end user's comfort and with minimal effort. The project has transitioned from lab to field testing and is now in the proof of concept stage. And the preliminary feedback has been pretty promising and positive from all stakeholders, showing there's real promise for utilizing these devices to optimize for cost and carbon. And that's all I had to talk through today. So happy to take any questions. If there are no questions, I have a few thought starter questions, but I will pause there to see if anyone had any questions they were dying to ask.
So great, Lucy. Super exciting and inspiring with the all the data that WattTime is able to collect. We have a few questions, but I just wanted to have one lead in here, which was, could you give a little bit of background on how WattTime collects this, like I guess the emissions that's coming out of WattTime's API and how you get that emissions data?
Yeah, actually, Henry, did you want to take that one? Is Henry on the line?
Is that better?
Oh, there we
Yep,
go.
I can hear you now.
Excellent. So we actually collect data from all the grid operators and then suck that into, like through various APIs, suck that into our system, and then we actually deliver that via the API, but we have various algorithms that actually look at for changes in load, how to changes in corresponding changes in emissions. And so we've actually built models across the US and actually across the world that are able to detect those changes in emissions. So it really relies on kind of foundational grid information. And so a lot of the grid operators provide enough information for us to begin to learn those things. Does that make sense?
Yeah, that makes total sense. So it's kind of like the slide Lucy had up before with what's like the marginal generation source. And so you're basically using an algorithm to detect that and use that as like a proxy for emissions, right?
Yeah, we actually have a lot of emissions-based information. We have generation by fuel. We have emissions from various fossil plants. We actually have a lot of the like very foundational information. The EPA is a great resource for individual power plant emissions. Don't tell the administration.
Yeah.
Otherwise, we might lose that data source, but it's a critical, all of those data sources are critical inputs to this process.
Amazing. Thanks so much. Yeah. John, you want to go ahead?
Yeah, my question was about where control of the compressor versus the electric resistance element lives in the control scheme. Is that WattTime's responsibility? Is it the OEM's responsibility?
Yes, in this case, it was, well, we actually provide a grid signal. Um, UC Davis was building the control algorithm, and then the OEM was responsible for delivering that schedule to the device. And I think there was like some settings that they used to like control when the resistance heater came on. And I think it was limited the use of the resistance heater.
Okay, thanks.
Well, and these signals with Davis, yeah, so they're being sent through Ream's interface.
Yes. So I think that ensures that the OEM can control cycling on the compressor.
Yeah.
And so that's that way that like the manufacturer maintains their warranty and things like that. So that was the like stack. Like all the grid signals came into the MPC. The MPC suggested a schedule. That schedule was sent to the device, and the device still had discretion whether to disregard that signal or that schedule or not.
Essentially preventing short cycling.
Exactly.
Cool. Okay, yeah, great. There was some interesting couple points going on in the chat relating to volatility of curtailment. Stephanie, did you want to come on for a minute and just kind of talk to your point there?
We did chat about it a bit in text.
Oh, perfect. Okay, I see that. Yeah, so do you want to talk a little bit about that then, Henry, about kind of curtailment predictability? That was a great visual you had up, Lucy, before kind of showing the almost like thermal signal, right? The color scale. So if you want to, would you mind pulling that up again, actually?
Yes, let me get to that.
And the point that Stephanie and I were discussing was really that solar curtailment is much more predictable than wind curtailment. We know when the sun is shining, we know generally how much demand there is, and the interplay between those makes solar curtailment much more predictable. Wind Excess wind is just much harder to forecast. We have good predictions of how much wind there'll be, but sometimes those forecasts are incorrect and you'll have far more wind than you thought, and thus a great opportunity to sop up excess wind. Where it gets a little bit difficult is it can come in multi-day chunks. So you could have like 3 very windy days, a large tranche of not windy days, or demand is high enough that you don't see curtailment. And so fast responding systems can be really effective at sopping up that excess wind. Heat pumps
Got it.
could be a good source for that.
When you have day ahead or several day ahead predictions for wind, do you find that they're generally pretty accurate, or is there a lot of variability from your like weather predictions?
That's a good question. I would have to talk to our forecasting team. It's a known struggle. We have a couple techniques for dealing with the predictability, or unpredictability. Uh, and I think we actually think of forecasting not in accuracy, but in efficacy. So if you have a whole day of forecasts, do you pick the best or the cleanest 6 hours out of that day most accurately? So if the magnitude is incorrect, that matters less than the relative intensity of your prediction.
Understood.
Yeah.
Cool. Bruce, you had a question. You want to come off mute and ask that one real quick?
Hi, Henry, Lucy. So, here at the California Energy Commission, Stephanie and I work on the same team. We're in the Flexible Appliance Standards Office in the Load Flexibility branch. And of course, we've worked with, Stephanie particularly been working with WattTime in Midas. And Lucy, in that slide from WEC, you showed that they tested it there, the water heater. I wasn't aware. We've been working with the other lab out at UC Davis, in the CLTC, and where they do a lot of testing. But I wasn't aware what test procedure was used for this, since it involved load flexibility, being able to shift load. Not only it had to be connected, but it had to take the signal from, in your case, emissions or pricing, I suppose, and actually shift based off those signals. I was wondering how that test procedure was developed, or was that just done at UCD and you just took their data?
In the lab test, I believe they wrote up a schedule for actual water use and then various. So I think there are two questions embedded here. There's one about test procedure and the second about baselining, because you have to know your performance compared to without the behavior. So for the test equipment, I think they had various schedules that they were testing for water draw. So they had a system for dumping water, and then they would just measure the energy consumption in response to that with and without a control signal. Does that make sense? And I'm not entirely sure of the exact water draw schedule they used, or I think they used multiple water draw schedules.
Yeah, no, I thought that the data output was how you shifted the use of the water heater itself based off of the signals for emissions. Isn't that what that slide was about?
Yeah, so I think that was the one piece, is like what test schedule. So what water draw, how did they measure the performance of the equipment? The baselining was actually developed in partnership with UC Berkeley's, what's the department in the College of Environmental Design? It's slipping my mind. The building performance department at UC Berkeley. They established a baselining method for dynamic baselines, for essentially for load flexibility, because a lot of the baselining approaches are like year over year or efficiency based. And so they worked to develop a really sophisticated baselining method for load flex. They actually used it in a building pilot. So for HVAC load flex, and I think they shared that with UC Davis, the WEC.
Okay. Yeah.
We'd be happy to make introductions.
Yeah, maybe at the WEC, that would be useful. If you don't mind, Henry, you know how to reach us. That'd be great. Thanks.
Absolutely.
Thanks. One last question from me here. I feel like we always talk about scalability on these calls too. So just kind of concluding with a question there. So for example, with your heat pump water heater shifting right now, would it be pretty easy to go from however many you're testing right now in a pilot to like sending signals to hundreds of devices? Does it take a lot of work for each one, or is it kind of a scalable signal?
So again, I think there are two questions embedded there. One is like, well, the signals are very scalable. We can send those to millions of devices tomorrow. UC Davis also, this is I think it's an EPIC project. So this is an open source project. And so all of the resources, all of the models. So not only are the MPC models open source, but also the cloud infrastructure. So if a manufacturer doesn't have the cloud infrastructure yet, they could piggyback on the work that UC Davis has done, set up their own systems, work with UC Davis for internal systems, work with various partners. So I think the groundwork has been laid to make this scalable. Again, the appetite for this from the manufacturers is key.
Totally. Great answer. Well, Lucy, Henry, thanks a ton. This was really great. Really appreciate having you on.
Thanks for having us.
Of course. All right. Well, I'm going to turn it over to Madison here to talk about some central heat pump water heater load shifting.
Thanks, Noah. Let me go ahead and get my screen up. Apologies, I promised we practiced this and now I'm...
No worries. That happens to me all the time.
Okay. Okay, can everyone see my screen?
Looks great.
Okay. So thanks everyone for being here. I'm Madison Johnson. I'm a data analyst at Ecotope. Our team conducts research that helps bring emerging technology to market. And so part of that work means that I get to look at a lot of commercial heat pump water heater measurement and verification data. So I'm really excited to be able to share that data with you all today. So a quick overview of the agenda. I'm going to be talking about 2 pre-monitoring metrics for quantifying load shift that Ecotope has developed. One of them is using Ecosizer engine, and then the other method is using the NIA single draw test. Then I'll show some examples of how these tests were applied in new demonstration projects and talk about some load shift performance from a brand new case study. And then I'll talk about next steps for improving these metrics. So Lucy did a really good job queuing up this topic, so I'm sure everyone on this call is really familiar with the fact that commercial heat pump water heating systems are a really valuable tool for utility companies. This graph shows a typical domestic hot water usage profile for multifamily buildings in the solid line. And we can use the large thermal storage tanks that heat pump water heaters have to shift heat pump runtime to off-peak periods and make our demand look something more like the dashed line. So this is going to minimize our energy consumption when the grid needs it most and when electricity is more expensive. But the questions we want to answer are, how do we know how much load shift potential a system has before it's installed? And furthermore, what metrics can we use to incentivize load shift? So I'm going to jump into the pre-monitoring load shift metrics, which is how we answer these questions. So the first method that I'm going to talk about today is using Ecosizer engine. So this method can happen before an installation when a system is being sized. As part of the California Tech Heat Pump Water Heater Program, Ecotope helped develop a calculator to determine incentives for eligible buildings that install load shift capable commercial heat pump water heating systems in multifamily buildings. So users go to Ecosizer and they input system characteristics like building size, storage volume, aquastat fractions, and set points. And then the simulation tool outputs the system's thermal shift capacity and estimated shed duration. The thermal shift capacity measures the difference in stored energy from when the heat pump turns off in load up to when the heat pump would be triggered to turn on during shed operation. So thermal shift capacity translates to the volume of supply temperature water that the system can deliver during a shed period without the heat pump turning on. So this metric is calculated based on the storage volume, aquastat fractions, and set points. And then Ecosizer also outputs the estimated shed duration or length of time that we can expect the heat pump to remain off during a shed period that starts at 4 p.m. So this metric is based on both the building size and the primary storage characteristics. So while this tool was developed for the tech program, it's really valuable for predicting how much load shift capacity a system will have. And then here's a visual representation of that thermal shift capacity I was just talking about. On the left, we have a snapshot of what our primary storage tanks look like at the end of a load up period. So this is when our tank is fully charged. And then on the right, we have a snapshot of what the tank might look like at the end of a shed period or when the heat pump needs to turn on during shed. So our thermal shift capacity tells us how much stored energy this system provided between this load up off state and the shed on state on the right. So here's an example of what an Ecosizer engine run looks like. On the left, we have a 24-hour simulation. Our top plot is showing the domestic hot water demand in blue and the available storage throughout the day in green. In that gray bar, which is our designated shed period, we're kind of coasting through that energy that we've stored, which is yielding an estimated 144 kilowatt hours of stored energy, our thermal shift capacity, and a shed duration of about 6 hours. And then that tech page outputs something that looks a little bit like this. We have an annual average hourly energy use plot with our baseline energy consumption with no load shift controls in red, and then our energy consumption with load shift in blue. So we're greatly reducing the amount of energy we're consuming in our shed period. And then it also outputs that thermal shift capacity. So that was our first method for estimating load shift potential. The second method for estimating load shift capacity is the NEA load shift test. This test can be completed in a day during startup, and it has been incorporated as part of Ecotope's commissioning process for these new load shift demonstration sites. So our first step is to let the heat pump water heater settle under normal operation under 0 draw conditions. So we're just going to let the heat pump charge as it would in its normal operation. Then moving into step 2, after the system is off in normal operation, we send a load up signal to the heat pump water heater and allow the tank to charge fully. So we're not actually sending a particular schedule or shed duration. We just want to see what the tank is going to look like when it's fully charged. So we'll wait for that heat pump to turn off during load up. This one's also done in 0 draw conditions. And then the exciting part is step 3. Once we're fully charged, we send a shed signal to the heat pump water heater and start a draw period, where this draw flow rate is specified based on system size. And then during that drawdown, we track all the energy that's exiting the system until the heat pump water heater is triggered on in that shed state. So this is giving us our thermal shift capacity. So it's the same metric that EcoSizer is outputting. We're just measuring it in the field this time. So this methodology was first tested in the PG&E labs in California. This plot is a little bit chaotic, but this was our first iteration of this test. In the bottom row of the plot, we have a bunch of tank temperature sensors in our primary storage tank. We're basically charging up that tank, and then you'll see the tank draw down when we're doing our shed testing, and we repeat this process a few times. So this is the first iteration of the test developed in the lab. And so after we run the single draw test or use EcoSizer engine to get our thermal shift capacity, we are going to use NEA's qualified products list performance assessment data sheets to estimate electrical shed capacity. So electrical shed capacity is the thermal shift capacity or stored energy divided by the COP. So thermal shift capacity estimates how much electrical energy we can shift outside of a designated peak period. And we compute this value for both summer and winter. And then we also report our peak load reduction, which is our heat pump input power multiplied by the number of heat pump water heaters installed. So similar visual to the last one, but this time, instead of looking at the energy in the form of heat that we have in our tanks, we're looking at how much electrical energy was avoided between those two states. So that's our electrical shed capacity. And now I'm going to discuss a couple case studies and show some of that new load shifting field data. So we conducted these pre-monitoring load shift tests at 3 new monitored sites. The first is a QAHV in Portland. For this site, we had the advantage of doing prior demand response testing with the QAHV, but this is a new build and it's been slow to occupy, which means we're not seeing full domestic hot water usage loads yet. So this one is still in progress. And then the second site is a Nile E360 in Portland. This is a demonstration of a brand new technology, so we're still working out some connectivity and load shifting controls in the field right now, and we're seeing the same thing with low occupancy. So sometimes these sites take a little bit longer than expected to actually see results that we can compare to our pre-monitoring metrics. And then lastly, I'll go into a little more detail on this one, is the Lars eTherm in Sacramento. This one is a retrofit, which is great because we don't have to wait for the building to fill up with occupants. We have, at startup, we basically have full occupancy. So this one was really nice for the presentation, but it is a demonstration of a new technology. So of course, there's still things that we're working out. I promised Noah I would touch on this one. So even though we don't have full field results from the Nile E360 in Portland, I wanted to show how our pre-monitoring load shift metrics look at this site. This top table here shows performance data from the product assessment data sheet. So the E360 is expected to have an annual system COP of 2.6 in Portland, and then an equipment COP of about 4 in the summer and 3 in the winter. And then the bottom table shows results from our 2 methods for quantifying load shift capacity. This building is quite large, so it translates to a large primary storage volume and large thermal shift capacity. Ecosizer engine estimates about 423 kilowatt hours, and the single draw test estimates 371 kilowatt hours. I'm going to talk a little bit in a future slide about why there's a discrepancy between those numbers and how we're working on calibrating the Ecosizer engine. And so I don't have field results to compare this against, but I'm going to talk about in the next slide the Lars demonstration, which we will be able to see some field results. So here's some photos from our Lars eTherm installation in Sacramento. This installation was incentivized by the California Tech program, so they are getting paid to load shift here. A little bit about the Lars eTherm is that it uses CO2 as a refrigerant. It has a maximum service water temperature of 180 degrees. It has an optional M&V package, which is really great. And it can do load shifting through Ecoport or a saved schedule. So we're looking at similar results for the Lars eTherm. We have an annual system COP in Sacramento, or projected system COP of 2.7. Ecosizer engine estimates that will have a thermal shift capacity of about 144 kilowatt hours, an electrical shed capacity of 44 kilowatt hours, and then in the summer, and then in the winter, that'll be 63 kilowatt hours. We typically see higher COPs in the summer and lower COPs in the winter. And so this is apparent in our electrical shed capacity. So the system is more efficient in the summer, so we have less kilowatt hours to shift outside of that peak period. And then this corresponds to a peak load reduction of about 30 kilowatt hours, and Ecosizer engine estimates that we'll be able to shed for about 5 hours. And this is brand new data, fresh off the press from August 2025. We actually only have a couple weeks of complete data at this site so far, so it's pretty exciting stuff to see. So this plot shows a 24-hour period with demand response schedules indicated by background colors of the plot. So in that 24-hour period, we have a load up period indicated in green from 2 to 4 p.m. And then we have our shed period in blue from 4 p.m. to 11 p.m. So the top row of the plot, we have system power. Our heat pump water here is in green and our swing tank is in yellow. The swing tank is disabled during shed at this site. So that one, it's locked out during shed. As we enter our green load up period, we see the heat pump water heater turn on and our heat pump stays on for most of that load up period. So it's charging up our tank. And then once we enter our scheduled shed period, we don't have any energy consumption from our heat pump water heater or our swing tank, which is really exciting. This is a super successful shed period. Then looking at the middle plot, this is showing our storage tank temperatures at various heights in the tank. As we enter that green load up period, you can see all of our storage temperatures rise. the top of the tank gets up to about 180 degrees. So we're storing a lot of thermal energy in this tank. And then once we enter that shed period, we're kind of coasting through that stored energy. And on this particular day, we still have quite a bit of stored energy left in the tank at the end of the shed period. So we're really not even reaching the full potential of what could be happening at this site. And then lastly, on the bottom plot, I always like to reassure people that the building is not being impacted by this load shifting. So on the bottom plot in that orange line, this is our domestic hot water supply temperature. So even though we've locked out the swing tank and the heat pump has stayed off for this 7-hour period, we are still supplying the building with 120-degree water. So there's no occupant discomfort here. And so in our about 2 weeks of data so far, we're seeing about 15 gallons per person per day based on our estimated occupancy. And this is translating to about 400 to 450 gallons of water during that shed period. And I was really hoping to be able to report the thermal shift capacity and electrical shed capacity that we're actually observing in the field. But because this installation is so new, we have a few things preventing a quality comparison. So why isn't this data apples to apples? So the test data that we showed in the previous slide was operating in an advanced load up, which means the heat pump water heater was actually supplying water at an increased temperature. So instead of the heat pump producing 160-degree water, we're actually producing 180-degree water, which is higher than we tested in our single draw test. So this is going to drive different storage temperatures and different behavior. We're also still working on refining the control logic and set points. As I mentioned, this is a brand new technology, so there's still a few things to work out. And then lastly is that extending the shed is possible. We're not capturing the full extent of that stored energy in our shed period. And then I'll talk a little bit about future work and improvements that we'd like to make to Ecosizer. So in the table with the Portland demonstration, we saw that Ecosizer engine predicts higher thermal shift capacity than what we saw in the single draw test. This discrepancy is primarily driven by the stratification profile in the primary storage tanks. So Ecosizer engine assumes perfect stratification, which means that the entire hot zone of the tank, or everything above the aquastat, is equal to the heat pump water heater set points. We know from field data and just from the control logic that when the heat pumps turn off, the lower zones in the tank are cooler than the heat pump water heater set point. We can see this in some field data from that first QAHV site in Portland. This in the top plot, the teal line is our heat exchanger outlet temperature. When our system is on, it's producing 150-degree water. Our warmest storage tank is at 150 degrees, but our middle tank and our lower tank, we see about 140 and 130 degrees. So this is going to drive a different stored energy than if the entire portion of the tanks were 150 degrees. So to account for this, the next improvement that Ecotope would like to make to Ecosizer is to introduce a stratification factor, which would help bring Ecosizer's estimates closer to what we see in the single draw tests. Additionally, this will better represent behavior in primary storage tanks for return to primary systems, which will be important for modeling and sizing return to primary systems, which have more destratified storage tanks than the swing tank systems that we've looked at today. And that's all I have for everyone. So I'm going to open it up to questions.
Thanks a ton. That was great. Love the Ecosizer updates and all the clear load shift graphs. I'll open it up for questions, but I had one thing first here. I know that Ecotope does a lot of design for the systems that you analyze before, putting them into the field, right? You kind of do both. And I was wondering if you try and optimize for like more storage than typical when doing like system designs and everything to better make this load shifting happen, or if you kind of just if it doesn't factor in as much, if it's just like a cost thing.
Scott, if you want to weigh in on this, I have a couple things to say, but Scott might have some things to add. I think it depends on the site. Sometimes we are restricted by the site itself. So one example of that is putting things on a roof. There might be weight restrictions, so we're limited in our storage volume in that situation. So our first load shift demonstration site in Seattle, that was the case, but we still saw really good load shifting results. And then for people who are designers who are sizing these systems, when you go to EcoSizer, you can actually specify how intense you want your load shift capabilities to be. If you only want to shift on, like, let's say you want to be able to shift on every single day out of the year, you're going to have to really increase your storage size, but you could get a better ratio of performance if you were to say, okay, I only want to be able to load shift on like 80% of days, for example.
Understood. So it's essentially assuming, especially like in the Northwest, that during winter days, because the COP is a lot lower, you probably can't shift as much, right?
Potentially, yeah, you might need to change your load up period or your shed period. You might need to change the schedule depending on the time of year.
Understood. Awesome. Any other questions, folks? Yeah, I love seeing these changes to EcoSizer. I think the stratification element would be really cool to see too. And once that's integrated, we'd love to have you or someone else from Ecotope back on to talk about that, because I know it's super critical.
Yeah, absolutely. It looks like Scott did drop a screenshot in the chat of that slider that I was referencing in EcoSizer, if anyone's curious.
Okay, sweet. Yeah, folks, definitely check out that tool. It's great to have the simulations too. But cool. Well, I know we're about at time here. Oh, thanks, Scott, for popping in that link. But yeah, thanks a million, Madison. This was great. Love to see the central heat pump water heater perspective too, and just how much load you can shift, right? I know you're mentioning like in the 30 plus kilowatt hours a lot of the time. So it's awesome for scalability, because even if you just have a few, it's so much load.
Yeah, absolutely.
Cool. Well, yeah, thanks again. Thanks to everyone for attending. And I'm going to stop the recording here in a second, but we'll post it out on YouTube, and see you in a month. I'm just going to check our calendar here. It will be October 3rd is the next session. So hope to see you there. And cheers. Thanks again.
Thanks all.